Consider a planar object. Planar means flat object. So this is the top view of the object, and this is the angular view. Fine. It must be a planar object. I'll tell you why it must be. Suppose there are two axes lying in the same plane as the object. Okay, and those two axes are perpendicular to each other. It is important to understand how the axis must be oriented and all. So let's say this is one of the axes. Some axis I'm taking, it need not pass through the center of mass also. Okay, and consider another perpendicular axis like this. You can call them as x and y axis. So basically, this is a planar system or a flat object lying in the xy plane. Okay, and if you imagine it from an angle, fine, where did we take the x-axis? Somewhat like this. The x-axis was somewhat like this, and y-axis was kind of like this, both lying in the same plane as the object. This is x, this is y. Okay, so when you see from above, you can understand that they are mutually perpendicular to each other. Fine. Consider a particle of this system. Let it be somewhere here. Assume this mass, its mass is m1. Now, system itself is in the xy plane, so the particle will be in the xy plane only. So this distance from y-axis, you can call it as x1. That's the x coordinate of the particle. And the distance from x-axis, you can call it y1. That's the y coordinate of the particle. So this particle is at the position x1 comma y1 in the xy plane. Okay. One of you tell me, how much is the particle's moment of inertia about x-axis? How much is this particle's moment of inertia about the x-axis?
m1 y1 square.
m1 y1 square. See, I want some others also to answer, like, I don't know. It's a basic question only, no? A particle's moment of inertia is what I'm asking. So you have to think, what is the basic formula for moment of inertia of a particle? It is mr square, mass multiplied with square of distance from the axis. Now I asked you, what is the first particle's moment of inertia about the x-axis? So you have to see how much is its distance from the x-axis, that's all. And that is nothing but y1. So its moment of inertia about x-axis becomes m1 y1 square. Okay. How much is the particle's moment of inertia about y-axis? Clearly, the distance from y-axis is the x coordinate. So this becomes m1 x1 square. Okay. Now imagine the z-axis also. Z-axis is perpendicular to the xy plane and it passes through the origin. So in the other diagram, it will be easier to visualize. The z-axis will be perpendicular to the system itself, like this. Here in the left side diagram, I can only show it with a cross. Okay, it's perpendicular to your screen. That's how the z-axis is. And you can even visualize the distance of that particle from the z-axis. You can call this as R1. Okay, I'll write it in black itself. Distance from the z-axis, let's call it as R1. Fine. Then moment of inertia of the first particle about the z-axis will then be m1 r1 square. Do you all agree with this or not? Distance from the axis is r1, so it has to be m1 r1 square only. But you look at this diagram and tell me, is there any relation between x1, y1 and r1? Let me show you the diagram separately. Is there any relation between x1, y1 and r1?
Pythagoras theorem, r1 square is
Good.
equal to.
Good. We can write r1 square is equal to x1 square plus y1 square. Correct. Now, if they are related that way, then we can relate the moments of inertia also. One of them has r1 square, one of them has x1 square, the other has y1 square. So r1 square is x1 square plus y1 square from Pythagoras theorem. Just multiply m1 on both sides. Then it becomes, or it changes to, m1 r1 square is m1 x1 square plus m1 y1 square. And m1 r1 square is moment of inertia of the first particle about z-axis. That is equal to moment of inertia of the first particle about y-axis plus moment of inertia of the first particle about x-axis. Is this clear to all of you? Simply by relating the distances from x, y and z axis, we are relating the moments of inertia about these axes. That's all, nothing special in this. Fine. Now, if this is true for the first particle, for all particles, you can write the same. Moment of inertia of the second particle about z-axis will be moment of inertia of the second particle about y-axis plus that of the second particle about x-axis, and so on. For all the n particles, you can write, and you add all these equations. What does the left-hand side become? Moment of inertia of first particle plus second particle, so on, all the particles about z-axis. So the left-hand side is moment of inertia of the entire system about z-axis. Right-hand side is moment of inertia of the entire system about y-axis plus moment of inertia of the entire system about x-axis. This is what is perpendicular axis theorem. You know x, y and z are mutually perpendicular to each other, no? That's why it's called the perpendicular axis theorem. And the system that we considered here lies in the xy plane. Okay, it's a planar system. And two of the axes, the x and y axis, lie in the same plane as the system. The z axis is perpendicular to it. Okay, so if you want moment of inertia about z axis, then only you can write it as, then it can be written as ix plus iy. Interchanging will not be valid. Okay, let's understand why it won't be valid. If you interchange, you'll get something like ix is equal to iy plus iz. Okay, let's see if that is true. Moment of inertia about x-axis is m1 y1 square. Moment of inertia about y-axis is m1 x1 square. And moment of inertia about z-axis is m1 r1 square. The only way x, y and r are related is r square is equal to x square plus y square. You cannot write x square is equal to r square plus y square. No, minus can be done, but plus cannot be done. Okay, so you can't write ix is equal to iz plus iy. That will be wrong. Fine. So there are some things that you need to be careful about while applying perpendicular axis theorem. The basic formula is iz is equal to ix plus iy. But that is valid when z is the perpendicular axis, x and y are the axes lying in the same plane as the system, not somewhere else. Okay, then only the theorem is valid. Suppose okay. Suppose the system lies in YZ plane. Okay, then the formula will be Ix is equal to Iy plus Iz. So basically what you need to remember is the two axes about which you are adding okay. So basically the two axes about which you are adding the moments of inertia must be in the same plane as the system. Like if the system is in the YZ plane, then you will add IY and IZ. On the left hand side, you will have the other value, other axis. Okay. And the other axis, the third one, which you are writing on the left hand side, must be perpendicular to the system. Okay. Now, why is this valid only for planar systems? What if it's not a planar object? See, suppose there is a three-dimensional object. Let's consider these X, Y, and Z axes from the angular view. Instead of being planar, assume this was a bulky system, three-dimensional. Now, if it is three-dimensional, you can have particles here also. Then its distance from the Z-axis will be this. Okay. Distance from X-axis will not be its Y-coordinate anymore. Okay. If you study 3D geometry, you'll understand. If the point is not in the XY plane, no. If point is somewhere above the XY plane or somewhere below it, then its distance from X-axis won't be the Y coordinate. It will be root of Y square plus Z square. Okay. How am I saying that? See, we took a point in the XY plane. Its distance from Z-axis was root of X square plus Y square. Okay. Similarly, if the point is somewhere else, okay, like here, then its distance from the X-axis will be some value like this, and distance from Y-axis will be some other value like this. They are not the X coordinate and Y coordinate of the object. Then R square is equal to X square plus Y square won't be valid if the system is not planar. Okay. So perpendicular axis theorem, the way it is derived, and for the formula that you get, Iz is equal to Ix plus Iy, it is applicable only to planar systems. Okay. Even compressing the system parallel to an axis won't work here. Because consider something like this. Suppose there is a point somewhere here, a point of the system somewhere here. It's exactly above the x. It's not on the x-axis, it's somewhere above the x-axis. Let's say there was a three-dimensional system like this. If you compress it parallel to the z-axis and make it planar, then you will see this particle falling on the x-axis. If particle falls on x-axis, finally Ix will become 0 for that particle. But initially it was not on the x-axis, means initially Ix value was there, non-zero value was there. Okay, anyway, this is slightly a deeper discussion. Need not worry much about it. Once you study 3D geometry, you'll understand much better. So compressing a system about a particular axis, no, what am I saying? Compressing a system parallel to a particular axis won't change its moment of inertia. That compression idea is valid, but you won't be able to use Iz is equal to Ix plus Iy in that case. Okay, because when you compress it parallel to z-axis, you'll be changing the distance from x-axis and y-axis. Okay, so Iz is equal to Ix plus Iy won't be valid. For the original system and the compressed system, it won't be the same. So just remember it this way, perpendicular axis theorem is to be applied only to planar systems. Fine. Let's discuss some applications of this. First one. Suppose there is a disk. Now we have derived moment of inertia of a disk about its own axis. But suppose you need moment of inertia about some other axis. What can you do? That is what we will discuss now. Assume this is a disk of mass m, radius r. Okay. Anyone other than Vanilla, tell me how much is the moment of inertia of a disk about its own axis? Uniform disk about its own axis. Moment of inertia of a uniform disk about its own axis.
Half mr square.
Mr square by 2, half mr square, correct. Now derive its moment of inertia about one of its diameters. How much is its moment of inertia about one of its diameters? I don't want you to derive it from the basics by using integration and all. You have to use some idea about moment of inertia to derive this. Okay, and remember, you know that moment of inertia about the z-axis here is mr square by 2. Try to make use of it somehow. Okay, can any of you tell me an idea to solve?
Iz equal to ix plus I.
Okay, you want to use the perpendicular axis theorem. Fine, that is one way we can proceed. We know the disk's moment of inertia about its own axis, and by own axis we mean the axis passing through the center of the disk and perpendicular to it. It's not in the plane of the disk, so I called it the z-axis directly. Now what you are asked to calculate or derive is its moment of inertia about the y-axis. Now you know that y and z-axis are perpendicular, so that's the hint that maybe perpendicular axis theorem can be used. But if you want to use perpendicular axis theorem, there must be three axes involved. Iz is equal to ix plus iy, right? So you need to take the x-axis also into account. Fine. Imagine the x-axis. Fine. And moment of inertia about this, let us call it ix. So we know ix is equal to iz plus iy. Let's see, what am I saying? We know iz is equal to ix plus iy because x and y are in the same plane as the system. We keep them on the right hand side. Z is perpendicular to the system. We keep it on the other side of the equation. Okay. The left hand side is mr square by 2. Iz. We don't know ix, we don't know iy. Our aim is to derive iy. Okay. Vanilla, don't answer. Others, any of you, will there be any relation between ix and iy? Do you see any relation between ix and iy? I mean, any similarity, or will there be a particular ratio, or is there any equation for them? Okay. The y-axis is a diameter for this disk. Okay, is the diameter of this disk. The x-axis is also the diameter of this disk. Iy is moment of inertia about that diameter. Ix is moment of inertia about this diameter. Now, moment of inertia depends on masses of the particles and how they are arranged around this axis. Now you all observe carefully and tell me, is the distribution of mass around the y-axis same as the distribution of mass around the x-axis or not?
Yes.
Saket, what do you think?
Yes, sir.
It's a uniform disk. All particles are similar. So you can see that for the y-axis, there is half disk on left side, half disk on right side. Okay, maximum distance being the radius, other particles are closer. Same is the case for x-axis also. No, half the disk is on one side, half the disk is on the other side. Then Ix, moment of inertia about x-axis, must be equal to Iy. We still don't know the value, but based on the distribution, we can tell that they should be equal. Okay, so if Ix is equal to Iy, then you can write the right-hand side as 2 times of Iy. That's all. Therefore, Iy becomes mr square divided by 4. So for a disk about any of its diameters, okay, you can take diameter at any angle. I mean, in any orientation, doesn't matter. Half disk on one side, half disk on the other side. No, all these axes will have the same moment of inertia because for all of them, the mass distribution is the same. Okay, it will be mr square by 4. Is this clear to all of you? Pawan, did you understand?
Yes, sir.
Yusuf?
Yes, sir.
Rishi, is it clear?
Sir, I have one doubt.
Tell me.
Doesn't the x-axis and y-axis extend like more and more? How is it just like the diameter of the?
Let them extend. They extend up to infinity. See, every axis extends up to infinity. But it's the okay, you are thinking that diameter should be only from here to here. Okay, fine. It's the
Oh,
diametric
but
axis.
yeah, but again, it'll still be the same. Yeah, I
It
understand.
will be the same. Yeah.
Yeah.
Okay. So for a disk about any diameter, it will be mr square by 4. How did we prove this? We use the perpendicular axis theorem. For a disk about its own axis, we already derived using integration. It was mr square by 2. We made use of that result and applied perpendicular axis theorem to derive this one. Okay. Now answer this directly or solve and tell me this quickly, all of you. What is the moment of inertia of a ring of mass m radius r about its diameter? Vanilla, don't answer, or you can type in chat. For a ring of mass m radius r about its diameter, how much is the moment of inertia? That's the question.
Sure, mr square by 4.
Think carefully and answer. Give your answers in chat. It's not mr square by 4. Saket, your answer is not correct. Pavan, Vanilla, your answers are correct. Okay. Yeah. Saket, unmute, we'll discuss.
Sir.
How are you trying to solve this?
Sir, I have no idea, sir.
Okay, fine. Fine. Rishi, how are you trying to solve this?
Sir, I'm not sure.
Yeah. Tell me what you know about moment of inertia of a ring. Like we had discussed ring case before also. What did we find out there?
Sir, that moment of inertia is like mr square.
About which axis?
About its own axis.
So we know that about a ring, and its own axis will be perpendicular to the plane of the ring. So you have to call it as the z-axis. So we know Iz in this case also, and we know that it is mr square. And Rishi, about which axis are you asked to calculate now?
About its diameter.
It's like the y-axis, no?
Yes, sir.
And y and z are perpendicular, so you can try to apply the perpendicular axis theorem. That's all. Same idea that we used for the disk in the last question. What you want is Iy. Consider the x-axis also, and the distribution of mass about the y-axis is same as the distribution about the x-axis. So you know Iz is equal to Ix plus Iy, and these two are equal. So you can write it as 2 times of Iy. That's all. Therefore, Iy becomes mr square by 2. So for a ring, about its own diameter, the moment of inertia will be mr square by 2. Saket, is this clear?
Yes, sir.
Okay. Now you all consider something like this. Just a moment. Okay. Actually, in questions, in your exam questions, they won't even give you the diagram. You only will have to visualize. Okay. So I'll just write the question here. Derive moment of inertia of a square lamina. Lamina means sheet. Okay. Of mass m, side A, about one of its edges, or one of its sides also we can say. Okay. Draw the diagram first, all of you. Visualize, draw the diagram, draw the axis about which you are being asked to find out the moment of inertia, and then solve. And till now, we have not derived anything related to a square sheet. Okay. So you have to use either integration or some of the ideas that we discussed about moment of inertia to solve this question. Okay. Think carefully. So imagine this is the square lamina, square sheet. Okay. And what you are asked to derive is its moment of inertia about one of its edges. Let's take this one. About any edge, it will be the same because the mass distribution about any edge is the same. Okay. Can any of you tell me an idea how to proceed? Because we cannot use any of the theorems. You can't use parallel axis theorem, nor can you use the perpendicular axis theorem, because we don't have any information about moment of inertia of a square as of now. So the theorems are not applicable. Can any of you tell me an idea to solve this? Okay. Rishi, tell me, what are some of the ideas we discussed about moment of inertia?
So can you repeat your question?
What are some of the ideas we discussed about moment of inertia, or some of the properties of moment of inertia?
If it's like symmetrical, it lies on the
That is center of
La-
mass. That is center of mass.
oh,
Okay, anyone? Can you tell me any ideas that we discussed about moment of inertia? Okay. One thing we discussed is if you slide the mass of a system parallel to any axis, its moment of inertia about that axis does not change. Okay, you can compress a system parallel to an axis. That can be done. And the other ideas, like I think that's the only idea we discussed till now about moment of inertia. Yeah, the other things were theorems. Fine. So let's see if that compression or sliding idea can be used in this case. Now you can see the axis here. It's like the y-axis. Imagine compressing this system parallel to the y-axis. What does it become, or what does it change into? It changes into a rod like this. Are you all able to visualize this or not? You just compress it parallel to the y-axis, okay, in its same plane. Then all the mass will fall onto a rod like this. Yes or no? It has to. It's like the projection of the square on the x-axis. It will be a line. Fine. Now the square's mass was m, its side was a. Therefore, this rod's mass will be m and its length will be a. And what we want is the moment of inertia of the square about that axis, y-axis, as you can see. Now, since the rod was formed only by compressing the square parallel to y-axis, the rod's moment of inertia about this axis will be same as the square's moment of inertia. And that rod will be a uniform rod because at every point of the rod, the mass falling is the same. The mass that is dropped onto every point of the rod is the same. So what the rod that forms is a uniform rod. Can one of you at least tell me this? What is the formula for moment of inertia of a uniform rod about an axis perpendicular to it passing through one end? We used it today itself.
ml square by 3.
ml square by 3. So Rishi, tell me, how much will be the moment of inertia of the rod about this axis in this case? How much is the length?
L.
Length is a, side of the square.
Yeah, sir.
So this becomes ma square by 3. That is for the rod. Then for the square also it should be the same, because the rod was formed only by sliding the mass of the square parallel to this axis. So they should both have the same moment of inertia. Therefore, the square also will have the same moment of inertia, ma square by 3 about this axis. Any doubt in this? Okay, next. Try to answer this directly, any of you. What will the square's moment of inertia be about this axis passing through its center parallel to two of its edges? How much will the moment of inertia be about this axis? Aishwarya, try to answer.
ml square by 12, sir.
It will be ma square by 12, correct? Because this axis becomes the perpendicular bisector of the rod. Fine. And for a rod about its perpendicular bisector, it is ml square by 12. Here the length is a, so it becomes ma square by 12. Okay. Next, for the square lamina itself, again, I'll just describe the situation. You visualize and try to derive, but you will have to make use of these results now. About one edge, it is ma square by 3. About the line which cuts the square into two rectangles, two equal rectangles, about that line, it is ma square by 12. Okay, we derived that by using that compression idea. Actually, there's another way. Integration idea is also there. We'll discuss that. But before that, derive this. Of a square lamina. Mass is m, side is a, okay? About an axis passing through one corner. Perpendicular to the plane of the square. Okay, visualize the axis carefully and solve. So basically, if you use this same picture, 1 second. This is the axis that we are talking about. Passing through one corner, perpendicular to the plane of the square means perpendicular to your screen. So if you visualize it properly, it's like this. If the square is in the XY plane, the axis that you are asked to calculate the moment of inertia about is parallel to the Z axis like this. So it's perpendicular to the plane of the square. Any answer, anyone? Or any idea? How can we derive moment of inertia of this square about this axis?
Parallel axis theorem.
Parallel axis theorem you want to use. Okay, if you want to use parallel axis theorem, one of the parallel axes should be passing through the center of mass. Where is the center of mass of a square?
A geometric center.
Geometric center. Okay. So in the right side diagram, let's visualize that axis also. And if you want to use parallel axis theorem, you need to know the moment of inertia of about one of those axes. Do you know the square's moment of inertia about this axis? We don't. So as such, you cannot apply parallel axis theorem because we don't know the moment of inertia of this square about an axis passing through its center of mass perpendicular to it. Of course, we derived moment of inertia about an axis passing through center lying in the same plane as the square. But now that result cannot be used here because this given axis is not parallel to this one. Okay, the given axis is parallel to this axis passing through center of mass. Through the center of mass, infinite axes can exist. Okay, and moment of inertia about all those axes also need not be the same. For a given system, ICM is not a fixed value. ICM means moment of inertia about an axis passing through center of mass, but through the center of mass also you can have infinite different axes. Okay? So ICM values itself can be infinite different for a given system. But yeah, good that you thought of doing it that way and we had this discussion. That's fine. Any other ideas, anyone, to derive moment of inertia about this axis? Sliding won't work because all the square is already in a plane perpendicular to the given axis. You can't squeeze it anymore. Like you can't squeeze it anymore this way. It's already flat. Okay, so those ideas won't work. But come on, I want one of you to come up with some idea at least. Yeah, one of you told parallel axis, it's not applicable, we showed. What is the other theorem we learned? There are only 3 ideas we learned about moment of inertia. That compression idea, compression idea, parallel axis theorem, perpendicular axis theorem. Now, compression idea and parallel axis theorem are not working. We are left with one choice, perpendicular axis theorem. We'll try to apply that. Now, the axis about which you are asked to calculate the moment of inertia, it's perpendicular to the square. So, if you want to apply perpendicular axis theorem, you have to call this IZ. Okay. And that can be calculated if you know Ix and Iy. Visualize X and Y axis. Here, in this case, X axis will simply be this edge. I'm sure some of you would have had some misconceptions. You might have been thinking that origin should be at the center of mass. Not necessary. For perpendicular axis theorem, center of mass doesn't matter. Okay. For parallel axis theorem, center of mass matters. So that is Ix. And this is the Y axis. About this axis, it will be Iy. So if you know Ix and Iy, you will be able to tell how much is Iz. You can visualize it in the other diagram also. This is the x-axis. And this is the y-axis. The square lies in the xy plane and you are asked moment of inertia about z-axis. So if you know Ix, Iy, you can tell Iz. Do we know Ix and Iy for the square? X and Y are like the edges of the square. Do you know moment of inertia of a square about its edges? That is what we derived in the last question, no? Ma square by 3. So we know Ix, Iy, both of them are ma square by 3 and ma square by 3. Therefore, about that perpendicular axis Iz, it becomes Ix plus Iy. The answer is 2 ma square by 3. So you have to think like this. You have to use one of the ideas to get to the answer. And there are only 3 ideas that we have discussed till now. That sliding idea or parallel axis theorem, perpendicular axis theorem. Is this clear to all of you? Any doubts in this? Aishwarya, did you understand?
Sir, can you explain it once more?
Okay, Rishi, keep yourself unmuted. What are you asked to calculate?
Sir, the moment of inertia about an axis passing through only one corner of it.
And how is it oriented? Passing through corner?
To the plane of the square.
Perpendicular to the plane of the square. Okay. So since the axis is perpendicular to the plane of the square, we can, like, it should automatically give you a thought that maybe perpendicular axis theorem is applicable. And since the axis is perpendicular to the plane of the square, what you are asked to calculate is moment of inertia about the z-axis, Iz. And you know Iz will be Ix plus Iy. So we visualize the x-axis, y-axis, and then we realize that we already know the moment of inertia about x-axis and y-axis. That is the last problem that we solved. Moment of inertia about y-axis is ma square by 3. For this, about this also, it will be the same ma square by 3 because that is also an edge of the square itself. So ix and iy are both ma square by 3 and ma square by 3. Then the given axis, which is the z axis, will be 2 ma square by 3. Clear?
Yes, sir.
Okay. Now try this question, all of you. For the square itself, okay, you can take a screenshot of this if you want, or you note down this result. About edges we discussed. About axis passing through the corner perpendicular to the square we have discussed. Okay, we have derived. Now derive the square's moment of inertia. Okay, it's still a uniform square plate of side A. Derive its moment of inertia about an axis passing through its center perpendicular to the square. This one. Okay. See, now also you are asked moment of inertia about an axis perpendicular to the given system. So maybe you can apply perpendicular axis theorem. So let's visualize the x and y axis first. The axis about which you are asked is the z axis. Okay, so you need to calculate iz, but we know iz can be expressed as ix plus iy. This is a planar system. For planar systems, you can use perpendicular axis theorem. Okay, but you will be able to apply it and derive iz only if you know ix and iy. And this we have already derived. Ix or iy, basically they are lines cutting the square into two equal rectangles. And for a square about that line, it is ma square by 12. Simple. So ix is ma square by 12. Iy is also ma square by 12. Add both, you will get iz, ix plus iy, 2 times of ma square by 12. The answer is ma square by 6. Simple. This is by applying the perpendicular axis theorem. But see, the axis about which you are asked to find out the moment of inertia is passing through the center of mass of the square. So maybe we can apply the parallel axis theorem also. Okay, let me show you how to solve it that way. Now the given axis itself is the axis passing through center of mass. So what you are asked to derive is ICM. How will you derive ICM? In parallel axis theorem, you have ICM. Okay, I is equal to ICM plus MD square. Now what you want to derive is ICM. Then you need to know moment of inertia about some other parallel axis. And from that you have to subtract MD square on the left hand side. Then you will get ICM. Let's see. Do we know moment of inertia about any parallel axis? Yes. The last problem that we solved, we know the square's moment of inertia about this axis. So I is known to us. And how much was it in the last problem? 2 ma square by 3 is what we got. And from this you have to derive ICM. Okay, so it's the reverse application of parallel axis theorem. You can do that also. But for that you need the distance between the two axes. Can one of you quickly tell me how much this distance will be from the center of the square to one of its corners?
A by root 2. Sir.
Yeah, total diagonal is a root 2. This will be a by root 2. So the distance between these two parallel axes is a by root 2. We will apply the parallel axis theorem now. Therefore, we can write I, which is 2 ma square by 3, I is equal to ICM, that is what we need to calculate now, plus m d square. How much is d? A by root 2, and you square it. Therefore, we get the required ICM as 2ma square by 3, and on this side, a by root 2 whole square is a square by 2. Send it to the left hand side, minus ma square by 2. 3 and 2, the LCM is 6. It becomes 4 minus 3 ma square. After taking LCM, this is what you get, and the answer you get is ma square by 6, which is the same as what we got using the perpendicular axis theorem also. Ma square by 12 plus ma square by 12 was ma square by 6. Even if you use parallel axis theorem in reverse, you will get the same result. And see, this is what makes moment of inertia an interesting quantity. There are many different approaches you can take to solve one problem. Okay, and that is what they like to test, whether you know how to look at it from all different angles or not. Okay, whether you know how to solve it using different approaches or not. And I told you I will explain how to derive moment of inertia of a square by using integration. We'll derive it first, and then I'll tell you why you need to know the integration approach also. Not just for a square. We are discussing some ideas, applying it to a square, that's all. So suppose you are asked to derive the moment of inertia of a square plate or a square sheet about this axis. Okay, now it's a continuous mass distribution. Can one of you tell me the basic formula for moment of inertia of a continuous mass distribution? By definition, what is the formula for a continuous mass distribution?
Integral r square dm.
Integral r square dm, correct. I told you there are two ways of applying this. One is you can choose some particle, call its mass as dm, then take the distance as r and proceed. But since this is an aerial mass distribution, selecting particles will be difficult. Okay, you can't take it as a collection of single particles, individual particles. What is the other way to apply this formula? Fix a distance first. Fix a certain distance from the axis, and at that distance, look at all the mass that is present. Okay, so let's fix some random distance from the axis like this, r. Now at that distance from the axis, what all mass or how much mass is present? This entire mass is present from this line to the next line. So you can say that this rectangular strip, in fact, the width, if you ignore, or if you assume the width tends to 0, this is like a rod. Okay, so this entire mass, you can call it dm, is at the distance r from the given axis. Okay. So what we now need to do in order to integrate this is to express dm in terms of dr. What is dr? Visualize. Dr is a change in r. We took r as this horizontal distance, then dr can be taken as the width of this element that we took. Okay, we visualized some particles which are lying at that distance r. Those particles occupy a small width dr. Fine. We need to express mass in terms of that width. Generally, whenever you need to express mass of some part of a system, you first look at what kind of distribution it is. We know square plate is an aerial distribution. Okay, so you have to write dm, small mass, is aerial mass density into area of the element, where aerial mass density is nothing but total mass by total area. Fine. That is why I said, like when we discuss these ideas in center of mass, that time itself I told you we'll be applying this very frequently. Okay, especially students preparing for JEE. Okay, this is like very fundamental in whatever we are going to derive from in all the chapters from now onwards. Taking element, expressing its mass in terms of total mass of the system, all those things. Okay, fine. And you can see that the shaded region occupies some area. That area is dA. Can any of you tell me the shape of the area occupied by the shaded region? In what shape is the shaded area?
Rectangle.
Clearly a rectangle. And how do you express the area of a rectangle? Its length multiplied with the width. Now the total length of the rectangle is the side of the square itself, A, multiplied with its width is dr. Therefore, the area can be written as small a into dr. That's all. We got dm in terms of dr now. We can write dm is equal to total mass by total area of the square into area of the element. One a gets cancelled. So dm is m by a dr. Okay, we'll substitute that in the integral. Therefore, I becomes integral r square into m by a dr. M by a, I am putting it outside the integral because they are constants. Dr. Fine. So that becomes m by a. Integral r square dr is r cube by 3. Okay. Now the limits for small r. Tell me, if you want to cover the entire square, small r should vary from which value to which value? Vanilla, don't answer. Anyone else?
0 to r, sir.
Where is r? I'm asking you the limits for r. Answer carefully. 0 to?
dr.
Rishi, dr
No,
is just...
no. Sir, is it a?
It is a. You have to cover all the rectangular elements like this, starting from the first one. The first one will be here. I'll show it to you. Its distance from the axis will be 0. That's the first rectangular element. And the last rectangular element that you take will be like this. Okay, which is at a distance of r from the axis. So initial one distance is 0, last one distance is r. Sorry, I made the same mistake. It is at a distance of a from the axis, side of the square. So the limits will be from 0 to a. That's all. Now you substitute. It becomes m by a into a cube by 3, which is effectively m a square by 3. By considering it as a rod also, we got the same result. In today's class itself, we did that. We got it as m a square by 3, about one of its edges. Using integration also, we get the same result. Now, why did I explain the integration method when the rod method was so easy? Because these ideas that we used till now, that compression idea and all, I told you, I mean, we verified also whether this rod is going to be uniform or not. Okay. For uniform rod, we know the result, so we were able to solve it. Suppose they give you a mass distribution whose density varies from distance to distance. Okay, some particles at one distance are light, and as the distance increases, suppose the particles become heavier and heavier. Then you will have to solve it this way. You can't use the rod idea. Because suppose the density increases from distance to distance. Okay, I'll try to show you a diagram. You all make a note of this.